Now if you go to the resources page on 721, some of you have seen these because I've seen you going through them. But if you go to the module resources page, I'm going to talk to you, the module resources page, and you go to the bottom of the module resources page, there's all manner of things down there that are going to put things in context for you. But the one down the bottom there, how simulators work, is probably one of the most innocent looking documents, but it explains absolutely everything that you're doing. Okay, quiet please. Thank you. So, you've all heard of Kirchhoff's voltage law and Kirchhoff's current law, right? So the sum of the voltages around the circle sum to zero. You know that. And the current entering a junction equals the current leaving a junction, right? Yeah? So all the simulator does is it uses this, and I'll put it on the board, look. So all it does is it does either mesh analysis or nodal analysis. And it loads it up into a matrix. Now, as you can see, there's various ways of solving that matrix. Just as we have V equals I times R, we can set up a matrix of V's, a matrix of I's, and a matrix of R's, and we can resolve as we go around a particular loop. Okay? And that's exactly what the simulator does. And this is SPICE. Not the horrible stuff that they use in prisons, but SPICE, that was a simulator that was written about 40 to 50 years ago. And what it does is it takes a schematic. In the old days, it used to take you would have to load the matrix in yourself. But now at least it comes in automatically from using a user interface. Okay? Now it loads it into the matrix according to the set of rules, and it solves for these equations. And it's using nothing more than Kirchhoff's voltage law and Kirchhoff's current law. And you can see another example down the end there of nodal analysis. You haven't got to remember this. I can't remember it. I had to look it up before I could even remember it. That was good that I did last year. I just put that up. So have a little look in that document. If you don't understand it, don't worry about it. But it's just Kirchhoff's voltage law and Kirchhoff's current law applied to matrix algebra to solve a circuit. Now you know from when we did the potential divider that I can come up with an equation for V out versus V in. And it's the same with any circuit. As long as you go around one particular node, one particular loop, you can move on to the next loop without violating any rules at all. And that's all you do. Okay, so you've got a circuit there and it's got hundreds of closed loops in it. That means that you've got a matrix that's hundreds by hundreds. Doesn't matter, computers are very good at solving that. So that's literally all that happens. But one of the problems that we run into is that most of these things want impedances to be able to do the evaluation, because as you go around a loop, as you trace around the loop, you're going to come across a component, right? That component can either be a resistor, a capacitor, an inductor. What's the other one? There's one more.
Source.
What do we say capacitor? Passive component or active component? No, it's one more. It's called a memristor. And they can make memristors, but they're really tricky things, and you need sub-zero temperature and all the rest to be able to make them. But it's a resistor that remembers its last state, and it's the last component. We don't model those. They're kind of theoretical, those ones. But what we can do is we can say that when we do our matrix multiplication, addition, subtraction, all of the stuff that we do in standard mathematics, what we can do is we can say we've got a resistor, we can say the Z, if you like. Z is just another word that we're going to use for not resistance, but impedance. So what's the difference between resistance and impedance? That's quite a tricky one to answer, really. Difference between resistance and impedance. Okay. Resistance is going to stay constant regardless of the frequency. Impedance is going to change as a function of frequency. So what that means is the ideal resistor, it doesn't matter whether you're using that ideal resistor at 1 megahertz or 1 hertz. It makes no difference. It's still got a resistance of 10 ohms if it's 10 ohms or whatever. Okay? That's not true with an inductor. Can someone tell me the equation for the inductor? That will give you the impedance of that inductor. Notice it's frequency dependent. And notice it's got 2 pi. Well, that's just because the sinusoid, or the cosinusoid goes round a circle of 2 pi and it's gone up and down once in that 2 pi. So that's what that's for. F, frequency. L doesn't change, does it? Right? So what I'll do for the time being is I'll just cheat and I'll say, well, actually 2 pi F, I'm just going to call that S. Because I'm going to put it into what's called the Laplace domain and I'm going to call that SL. For my own convenience, well, Laplace taught us to do that and there's some quite nice proofs of how you can go from that to that. Now if I say the Z of a capacitor, you've got it, 1 over 2 pi FC, and that looks like this, which now means that we have that. So wherever in a circuit, when I'm doing my SPICE models, whenever multisim is doing it, when it sees a capacitor, it replaces it with this. And when it sees an inductor, it replaces it with this. It's called generalized impedances. So the impedance of the inductor is represented by SL. The impedance of the capacitor is represented by 1 on SC. Suddenly this isn't calculus, it's algebra. Now calculus is difficult to solve because you have to differentiate multiple times and so on and so forth. But with this, all you're doing is a little bit of algebra and out of it falls the answer. So that's great, so that's why we want to do that. So where does this really come into play? Well, we know, we saw this simple circuit that we did before, didn't we? So we had this and you built this filter, remember? So it's V in, that's V out. And inside there, or in here, you're going to inject a sinusoid. And intuitively, what's going to happen there? Well, intuitively, at high frequency, this is going to go short circuit. So you're going to get nothing at the output at high frequency. At low frequency, this isn't even going to be there, analogously. So you're going to see all the output. So it's going to let low frequency through and block the high frequency, right? Yeah? Now let's do what the simulator might do for that. So let's say that's 1 on SC, and that's R. Well, what I can say is we know that for a potential divider, V out is equal to V in R2 upon R1 plus R2. One of the most important equations you'll ever come across in electronics, second to the diode equation. Now, if we want to do that, well, we can just replace them. So R2 is 1 upon SC, R1 is just R, and R2 is 1 upon SC, right? So that's messy. Why don't I multiply through by SC, top and bottom? In which case I get 1 upon SCR plus 1. What does that tell me? That tells me is the complex frequency, because this is complex numbers by the way, it's not just real along that line, it's real and imaginary because you're tracing out a sine wave. 1 upon SCR, what does that tell me? It tells me as the frequency gets high, the output gets low. And as the frequency is low, the output is close to 1, which one that I put in the first place. You can do that the other way. So we can say, and it's the same for the inductors, I'm not going to do it for the inductors, but this one here is a high pass filter, and that's 1 upon SC, that's R, and I can do the same thing as I did before, so it's R2, which is just simply R upon 1 upon SC plus R. It's a bit messy, so I'll multiply top and bottom by SC, and I get SCR over SCR plus 1. And if you follow through the same logic at high frequencies, the 1 is going to become insignificant, and at low frequencies, well, work it out for yourself. Okay? But remember, the simulator is just taking all of this kind of knowledge that you can replace this, because this is an integral equation, and it's very, very difficult to deal with mathematically. You can do it all in calculus, but you don't want to, and that's what Laplace did for us. That was magic, and said, well, I don't want to work on calculus, I want to work on algebra. And as soon as we work on algebra, then we can do matrix manipulation, then we can solve for any case. Now, while your simulator is running, when it's plotting a sine wave on your oscilloscope or whatever, it's solving that matrix thousands of times a second to be able to do that, but it's still using very, very basic building blocks to be able to do it. Okay, so just have a look at that under the resources. Like I say, you don't have to understand it, but it's just useful from the perspective of where do all these things come from. And as with all things that humans do, it's not somebody just came up with this brilliant idea overnight. This is incremental over the last, well, I said the spice has been about for 40 years, but people have been doing matrix algebra like this for electronics for well over 100 years. But all they're doing is just building on the building blocks that they had to start with. Okay? Carry on with your designs then.